Alright, in today's video we're going to be covering sections 12.1 and 12.2. We're going to start off actually doing a little review of integration, since we're going to need all the techniques we had in Calc 1 and Calc 2 to do these integrals. Then we're going to define double integrals, just using the same ideas we had from Calc 1. And then we're going to go over how to actually do some computations over rectangular domains. Alright, so let's get into it. So first things first, let's do a little integral review. If you feel pretty confident on your integration, you can skip this. There'll be little timestamps in the description in the video, so you could just skip ahead past this. But if you need a little review, then we should go through this. So just a couple things just to try to remind you. So when we have an integral, if we have x to the n dx, then this is going to be x to the n plus 1 over n plus 1. So all of our integrals that we're going to be doing in this chapter are definite integrals. In chapter 13 we can talk about indefinite integrals, but we're not going to have too much time to get into that. But in general, still, you got your plus c. And again, this always works except when n is equal to -1. So that's this scenario where we get natural log of x. So just a couple other quick ones: e to the x, z to the x, sine. Alright, we've got cosine. And just as a reminder for all of these, just make sure you remember that you can always go backwards to check yourself. So for example, the antiderivative of sine, that's negative cosine x. And I know it's that because if I take the derivative to try to go backwards, well, the derivative of cosine is negative sine, so the negatives will cancel and I'm good. Similarly, I know that that's sine x, because if I take the derivative back, I would get cosine. So there's a whole bunch of these that we could all go through, but it's just a kind of quick reminder. The other couple things we need to try to remember are some of our special rules. So we had u sub, right, and an example of this that's actually going to come up later, something pretty similar to this. So we've got x squared plus 1 squared. We can do u equals x squared plus 1, du is 2x dx, move the 2 over, and this integral becomes u squared du over 2. I can move the 1/2 outside, and now I'm just back to this scenario. Another thing that's going to pop up is if I have bounds, I need to change the bounds. So as an example, if I had the bound 1 to 2 to start this, and then when I'm doing my my u sub, I need to change the bounds. So remember, this is x equals 2 and x equals 1. So then my bounds would then become, well, I'd plug 1 into here for x, and that would give me 2 now, and then I plug 2 in for x, and that would give me 5. So my new bounds would be 2 to 5. Okay, the other thing we're going to need, and anything else that pops up, I'll just do a little quick overview of it, but this should get us started, is integration by parts. So remember, integration by parts, we're trying to pick a u and a dv, right? So we pick this. Step 1. Step 2 is we do du and v. And then step 3 is we do uv minus the integral of v du. So just kind of quick little example, the integral of x e to the x. So the way we could pick this, so there's a bunch of these: Lipit, Elliott, I like Lipit better, it sounds better, log, inverse, trig, polynomial, exponential, trig. So this is how you pick u. Doesn't work perfectly all the time, but it does a pretty good job. So there's no log, there's no inverse trig. Polynomial is the first thing I see here. So I would make that my u. Take the derivative. Don't forget your dx here. Do the antiderivative. And then I would plug into the formula uv minus the integral of v du. And now I've gotten to an integral I can do. So super fast, super quick. Any of these things you don't remember, you got to just go practice them. Try to take some time each day you're studying to practice a couple of integrals. Just go into the book, into earlier sections, and get some of those down. Just go to the exercises and try them out. Okay, so next thing is to introduce double integrals. So the way that we're going to do this is by first reviewing how we defined an integral in Calc 1. So an integral in Calc 1, just to write it out, and we're going to be doing definite integrals here. Looks like this, right? So I was integrating in Calc 1 over this interval from a to b. So this is just a little line segment here, a little interval on the x-axis. So I was integrating a function, that's my function here, f of x, over that. Now when f of x was greater than 0, this represented area under the curve, right? And the way I did this was I said, okay, I'm just going to approximate this by creating a bunch of rectangles that fit under the curve or partially under the curve. And each rectangle will have a height that's determined by the value of the function at some point in the rectangle. So you give me some point, you give me some point in the rectangle, or in this little width of the rectangle, and I will tell you how tall it is. Then all I do is I take that height, I multiply it by the width of the base of the rectangle, which is our delta x, and that gives me an approximation to some of that area there. And then I just add up each of these rectangles, add up all their area, and that's my approximation. So we said that that's pretty good, but if I let the number of rectangles get bigger and bigger and bigger, which means their widths are getting small and I'm fitting more of them into this picture here, then eventually, I'm never going to hit it, but the limit of that action will get me to this integral, which will get me to that area. So the area under this curve is the integral, which is the limit, as n goes to infinity, of this process of adding up a bunch of rectangles, bunch of areas of the rectangles. So here's the idea. If you feel comfortable with that process, that idea, then all we're going to do, just like we've done in this class many times, is we're just going to bump this up. And so what I mean when I say bump this up, it's the same as how we've bumped up everything else. What did you need to do this integral? I needed to give you a function, and I needed to give you a domain to integrate over. So what I'm going to have to do when I do a double integral, I'm going to have to give you a function, and I'm going to have to give you a domain. What changes? So if this is the 2D case, now when we're in 3 total dimensions, I'm going to have to give you a function of now 2 variables. Whoops. Definitely don't start at 2. So I'm going to have to give you a function now of 2 variables, and my domain, which was x as before, is still a domain, but now it's x and y's. Alright, so it's going to be a little more complicated. We're going to start with the simplest case. So the simplest case is we take an interval in x and then an interval in y. So it's really just in the Calc 1 case, it was I integrated from a to b. Well, I'm just doing that, except for now I'm going to also integrate from c to d. So the next step from an interval in one dimension is to add on another interval in the other dimension, and when I do that, I create a rectangle as my domain. So what we're going to be doing now is taking a function, so f of x comma y, which when we graph this will create a surface. That's this blue here, that's a surface. And what we're going to do is we're going to try to find out what the volume under that surface is. So again, what did we do before? It was area under a curve. Bump up another dimension. Bump up. It's volume under a surface. So just that next step. And the really nice thing about the construction of all this is it's the same idea. Before, what did we do? We took our interval, right? We broke it up into a certain number of pieces. We took points inside here, right? We tested those points along the curve, whatever that looked like. And then we drew these approximating rectangles in here, right? So same idea. I'm going to take my region, I'm going to chop it up into pieces. And what you can think of is, well, how do I chop this region up? It's the same way you would chop up the region in 1D. It's just that you do it to each of these smaller one-dimensional segments. So I chopped up this like this. I'm going to chop this one up like this. Same idea, it's just I'm doing it to two of them now. And what that does is it gives you this little pattern, this crisscross pattern on the rectangle, which you can see here. And all of these little dots in here are just my little test points for each of these rectangles. And what I'm going to do is, for each dot I pick in a rectangle, I'm going to take that dot, so maybe that looks like this dot here, and I'm going to go up to the function, maybe that hits here. I'm going to see how high that is, and then I'm going to create a nice little column here all the way down. So instead of an area, trying to approximate an area with rectangles, I'm going to approximate this volume with these columns that are pictured right here. So a bunch of these different height columns. Now, if you're thinking, wow, where is that column coming from? Again, all I'm doing is I'm taking this rectangle, right, and I'm going add a dimension. When you take this rectangle and you add a dimension, well, it's already got 1, 2 dimensions. So if I add a third, I have to just go back this way. And what did I create? A column. And instead of its area, I'm going to have its volume. So above, what you should visualize is this picture here. Above each of these rectangles sits one of these columns, and it's trying to fill up the volume under this surface. And it's the same exact scenario. The more I chop up this region, if I make it even more of these columns, more columns, then I'll do a better and better job approximating the volume here. And so that's the way I'm going to define a double integral, is this process of chopping up my region, creating a bunch of columns that fill in the region, and then letting that process, letting the number of those things go to infinity. So let's just rewrite that. So again, Calc 1, I chop up my interval into a bunch of pieces, a bunch of parts. For each one of those, I fill in a rectangle. I look at its area, right? This is the area of the rectangle. I add all those up, and that's my approximation. How do I get the integral? I do that process, but I let the number of rectangles go to infinity. That limit is my integral. So, how do I do this in 3D? Well, start by doing an approximation. I'm going to, again, chop up my interval, my rectangular interval R. I'm going to, instead of a rectangle, I'm going to have a column that has a volume sitting on each one of those, right? And then I'm going to add all those up. That's what this process is. This is me telling you add them all up. This is the height of the column. and this is the area of the base, which you can think of as delta x times delta y. All right, so then how do I get a double integral? Well, I think about this process that we just talked about, and I let the breakup of the x and y go to infinity. So what am I doing? I'm saying, okay, I'm going to make m rectangles in the x direction, n rectangles in the domain, chop, 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 in the y direction. Now, if I let both of those go to infinity, more and more and more and more, and I add that up, I'm going to get the integral. So what you should really focus on is the parallels between these two constructions. Very, very, very similar. They're both trying to measure something. Area up here, volume here. They both involve limits, more and more and more, chopping up of your domain that you're looking over, and you get an integral at the end. So what we should do now is talk about, how do I do computations here? How do I use this, right? So when you first were introduced to this in Calc 1, and you did some approximations, it probably seemed terrible. But then you learned rules about these integrals, and through those rules you were able to figure out a bunch of problems, do a bunch of computations. So that's our goal now. Can we do a bunch of computations with these integrals? So let's think through this. All right. So that's all 12.1. You know, pretty straightforward, not too bad, the idea of it. It's just, here's what the integral is. There's not too much in terms of problems I could ask you to do from that. It's just, can you understand the construction and what this means? Now 12.2 is where we get kind of down into trying to actually do some computations here. And the way we do that, it's really nice if you've gotten yourself comfortable with doing derivatives, the partial derivatives. It's the same construction, because of course it is. It's always the same construction. Well, what's the construction? If I start with the region R, so this notation, these are your x values that you can go between, and these are your y's. Okay. So I'm going from, and you can see that down here, I'm going A to B in x and C to D in y. Okay, so I want to integrate somehow over this, and I've got a double integral. So one with x, one with y. Okay, so what we should think about here is, well, how did I do this as a derivative? Well, when we did derivatives, because there were two variables, the only way to do this was to get ourselves back in Calc 1. And how did we do that? Well, what we did was we fixed one of the variables as a constant number. You just thought of it as a number. And then we did our Calc 1 on the other variable. That's exactly what we're going to do here. So what does that construction look like? So what I'm going to do is, taking the same picture as before, I'm going to fix a value for x. Let's call this value x bar. So I'm going to just fix some random value x bar in here. Okay. Now remember what happens when I do that. When I fix x as a constant, then this actually becomes f of this constant, which is really just now a single function of y. Because x is a constant, it never changes, so I just have a function of y. What I'm really doing here is I'm taking my surface, this blue picture here, and I'm slicing it with x equals x bar. Just like we were doing before, I'm just slicing. So when I slice this surface at this fixed x value, and remember, you can think of a plane cutting through here if you want, and all that's left when I have a plane that cuts through this is this purple section here. So when I have a plane cutting through here, kind of cutting through this, so I got a plane that's cutting through here, then what's going to happen is I'm just going to have this nice little purple slice left over. Okay, so what can I get out of that purple slice? Well, this is now a function just of y, because I can move in the y direction along here, so I can still move this way in the y direction. And well, what can I do? Well, I've got a function g of y, and I'm interested in this shaded purple region, that looks a lot to me like the area under a curve. And that's exactly what it is. Well, how did I do the area under the curve? I did an integral. This is the integral. I'm integrating this function. Remember, x is a fixed number, so this really is just a function of y. I'm going to integrate that with respect to y from c to d. That should give me exactly the area under this curve. So then, okay, that's good. I've got the area of this, completely thin slice, right? So then what happens? Well, depending on what x I give you, that's going to give you a different volume, possibly. So what you should think is, okay, I see that that purple slice, right, has a volume, but what if instead I was considering B? I wanted to slice at B. Well, the slice at B would just be, well, that's a bad color to pick. Let's try light green. The slice at B would be exactly this slice now. Right? So now I'm this slice. Okay, well, that slice looks like it might have a different area than the purple one. So you're giving me an x, and then I'm able to calculate a number and give it back to you. That's a function. So that's the function a, we'll call it, of x to say area. Okay, so now I've got a function a that takes in values, right, big A, that takes in values on this interval, right? And I'm interested now in the area under that curve. So I know that's a little tough to be thinking about, that exact idea here, but this is what we end up with. We end up with saying, okay, now this is a function of just x, and I want to add up all the values of that function, right? Because I'm basically just taking this slice here, and I'm saying, okay, that's good, but that's just one slice of this very large volume. Well, what I want to do is I want to add up all the slices, starting with A and getting all the way to B. And the way that we're going to do that is we're then going to integrate that function from A to B, but now with respect to x. So then we've just taken a double integral and done it in two steps. We first integrated with respect to y, fixing x. That's important. We fixed x, and we integrated with respect to y. Then we let x vary, and we integrated with respect to x. So when we do an integral like this, you read this as do dy first, then dx. When you're doing this dy, as the brackets suggest, you can just forget about everything else in the problem. So we're going to do some examples in just a second. You're going to integrate the inside first and go, ooh, Calc 1, I can do this. Then that will give you a number, because remember, here and here, this is a definite integral. So a definite integral will give us a number at the end. Now, when I say a number, I mean constant, which means it'll have no y's, but it'll only have x's left and actual numbers. Then that will get slotted right into a new integral from a to b with respect to x. I integrate that, all my variables are gone, I have a volume. So we're going to look at some examples where we have a volume because our function's greater than 0, and some where we don't. And we can look at some Mathematica pictures of that, which I'll post in addition to the slides. So let's see what we got here. So let me show you an example, and then we'll go back to Fubini's theorem, because there's some choice we have here that we have to think a little bit about. So let's just talk about setting this integral up first, and then we'll talk about Fubini's theorem. So there's two ways we could set this integral up. So remember, this is my x's and this is my y's. Okay, so then I never told you what the order of x and y was going to be, or should be. So you might think, well, I want to do it this way. And another student might say, well, actually, I want to do it this way. So how do I know who's right? Which order do I do it in? Well, when we have a function, remember this is always our function f, that is continuous on this rectangular region, it doesn't matter. We can do it either of these ways. So let's go back to Fubini's theorem. Just to restate it, Fubini's theorem says if f is continuous on the rectangle R, then it does not matter in which order I integrate. Doesn't matter at all. So what you should be thinking here is, oh yeah, I've seen something like this before in this class. Under some pretty similar conditions with continuity. So again, this is just reinforcing this idea of this mixing of x and y. It doesn't matter, you do it whichever way you want to. So, how are we going to apply this then to a problem? Well, what you're going to have to do is think to yourself, what will be easier? So this happened to us in Calc 2 when we were doing volumes of revolution. It was always what made things easier. Now, it's not quite as easy, actually, I think, as it was then to figure this out. What you're going to have to do is do a little evaluation of what steps you might have to take to do the integral. So just to give you an example of how I would do this. First, let's set up the bounds. So this would be x first, so that's 1 to 2, then 0 to pi. This is y first, so that's 0 to pi, and then 1 to 2. Okay, so I'm looking at this, and let's start over here. So what's my first step? Well, 2 slides ago we saw to do this integral, I just pick out the inner integral, and I do 1 to 2 of y sine xy dx. Okay, so what I'm thinking to myself is, this is what my integral is. X is my variable, y is constant. So we've done this before in terms of partial derivatives. So I'm just thinking of y as a constant. You can even actually move any y's that you're able to move out. So for example, if you really wanted to, I could take this y and move it outside the integral because it's a constant. In terms of this integral, just this inside one, because this says dx, that means my y is a constant. So we could take it out if we wanted to. So I'm looking at this and saying, okay, well, it's just a constant times sine of x times a constant. Well, I feel like I could just kind of do that one with a little trickery, but I should probably just do a u sub here just to make sure that I don't mess anything up. So we look at that one and say, okay, there's probably a u sub there. Well, let's hold on for a second. Let's go to the other one and see what this one looks like. Now I've got the integral 0 to pi of y sine xy, but now this is dy. So now y is my variable. So I'm looking at this and I'm thinking back to myself and I'm saying, okay, I've got a function y times a function sine of xy. That doesn't look great for a u sub. I don't remember any rule about multiplying these functions. This looks like this is going to be an integration by parts problem. So now it's up to you. Would you rather do integration by parts or u sub? The correct answer is u sub, of course. You could do it the other way. I would say if you need practice, go do integration by parts, but u sub is easier, so let's just do the u sub. So here's where it gets a little tricky, though. My u is equal to x times y, right? When I do du what? Well, I have to always go back to this dx here and say, what is the variable I'm looking at? The variable I'm looking at is x. So the derivative of this is actually the derivative with respect to x when I'm doing this here. So I've got to remember that. It's the derivative with respect to x. So this would be just y dx. X is just a variable to 1 power. I take its derivative, it goes away. Okay, but I'm actually pretty lucky, so I've definitely chosen pretty well because I've got y dx in here. So this substitution is going to work very nicely. So let's do it. This would be now the integral sine u du. Okay, that's pretty nice. Now, as we saw before with the review, I've got bounds, so I've got to change my bounds. When x equals 1, u is equal to y. And when x is equal to 2, u is equal to 2y. Okay, so then I'm going to do this integral. The antiderivative of sine is negative cosine of u Okay, so then that's now equal to negative cosine of 2y minus a minus, so that's plus cosine y. So let's get rid of that. Okay, so perfect. I've done the inside integral. Now, that has to be transported back here into that original integral. So that was 0 to pi. And inside that, we now have negative cosine 2y plus cosine y, all of that dy. Okay. So, again, though, I'm just a Calc 1 integral again. These aren't too bad to do. The antiderivative of cosine is sine, so this is a nice one. And again, this is actually a little u sub, but if you're quicker on the u subs, this isn't too bad to do. All right. Okay, so then we just have to plug in. All right, so we're at this point. We got to plug pi in, we got to plug 0 in, and we get 0. So check that for yourself. And I know that that is unsatisfying for some, but satisfying for others. We get 0 at the end of this. So what we should be able to do then is, and I'll post a picture of this, is we should be able to look at this function over this rectangle and get the picture that this function has just as much volume above and below the xy plane, so that it all cancels out. So we can check that later. Okay, next example. So how do we start this problem? Well, it's already set up for us, which is nice. We then ask ourselves, okay, I'm looking at this, is it better to do y than x or x than y? Now, I don't see any difficulty in doing any part of this problem really, in terms of these are all just x and y's to powers, and I'm not too worried about doing the antiderivative of that. So I think that this is fine. Let's just get started. So we take the inside integral, 1 to 2, 4x cubed minus 9x squared y squared dy. So I'm just taking the inside. Okay, so then remember, this is with respect to y, so this would be 4x cubed y minus 9x squared y cubed over 3 from 1 to 2. Okie dokie, so we got some cancellation here. That becomes a 3. So let's plug in. So this is 4 times 2 cubed y. Whoops, be careful. I would have pretended in class that I had done that on purpose. Or I mean, I did that on purpose. So remember here, these are all with respect to y. So what you could do for yourself to remind you, because it is tough to remember, is that that's y equals. Y equals. So I should only be plugging these things in for y. So this is 4x cubed times 2 minus 3x squared times 2 cubed. Okay, all of that now is minus 4x cubed times 1 minus 3x squared times 1 cubed. Okay, so that's 8x cubed, that's 8 minus 24x squared minus 4x cubed plus, because of the two negatives, 3x squared. Okay, that gives me 4x cubed minus 21x squared. So that was the inside. So now this needs to be transported back up here and plugged back in. Okay, so that's then going to give me the integral from 0 to 1 of 4x cubed minus 21x squared. Now dx. So at this point, we have no more y's anymore. That is what needs to happen. If you have y's still in your integrand, then you did something wrong, go backwards. But then again, this is just a Calc 1 integral. 4x to the 4th over 4 minus 21x cubed over 3. All of that from 0 to 1. Okay, little cancellation. So that's 1 to the 4th minus 7, 1 to the 3rd minus I plug 0 and I'm just going to get 0. So that's 1 minus 7 is negative 6. What that tells us is that this is not just a volume, because volume should always be positive. This function must spend at least some time below the xy axis on that rectangle. All right, next one. Uh-oh, so this looks like a little bit of a doozy. And again, we're looking at this and saying, is this the right form? Fubini lets me switch the y and x, because I'm on a rectangle and this is continuous on this rectangle. But at a closer look, the x and y can be switched around, right? So this x and y, I could flip-flop those, it doesn't matter. This x and this y could flip-flop, doesn't matter. The bounds are even exactly the same. So there is literally no difference in the way that I do this. But what you might want to do is, I'm going to go through and do it this way. You might want to flip these two for yourself. Try going through the problem and see if you get the same answer. So Fubini's theorem tells us we should, so this is just good practice to kind of go the other way, because everything will be kind of flip-flopped. So let's just give it a shot. Remember, I'm going to take the inner integral here. So this is 0 to 1, xy, x squared plus y squared dy. Okay, so now I'm looking at this and saying, well, what method do I have here? Well, I do see some function composition here. That could be promising. So let's try a u sub where this x squared plus y squared is my u. So then I'm going to do the derivative. Now, what am I doing the derivative with respect to? I just got to go back up here and say, oh yeah, I'm doing dy. Okay, so then the derivative of x squared with respect to y would be 0. So then that's 2y dy. I do not have a 2 in the original integrand, so I'm going to divide it over. Y dy. Okay, so then I'm going to do the substitution. So this is the integral. I've got x, but then remember y dy. So y dy is going to become du over 2. Okay, so then that would be x times the square root of u du over 2. Now, if this x is messing you up, we have something we can do with that, right? X is a constant in this scenario, so we can just get it out, move it out there. Okay, so then if we move that out there, and we can move out this 2, so, and we could have done that at the beginning actually, so that might be a step you want to take. So then that would be the integral x over 2 square root of u du. And now you might be saying, you're missing something. You're right. I've got to include these bounds, these original bounds. And the way that I do that is I have to run it through the substitution. So then, just to remind myself, this is y equals. So when y equals 0, u is going to be x squared. Oops, not there yet. Get out of there. X squared. Okay, and then when y equals 1, u is equal to x squared plus 1. Okay. All right, so let's do the integral. The antiderivative of square root of u, remember that's just u to the 1/2. So that's x over 2, u to the 3/2, and then I drop the 2/3 down here. Okay, x squared plus 1. So let's actually move this up to the top to give us maximum room. So I'm going to get cancel, and that'll be x over 3. I'm going to plug in x squared plus 1 to the 3/2 minus x squared to the 3/2. And you might want to put some parentheses around that. Okay, so now all of that is getting plugged back into the original. Right, so it seems like a lot, but we'll see it's not actually too bad when we get through this. So this is now integral from 0 to 1 of x over 3 times x squared plus 1 to the 3/2 minus, and I'm just going to do a little cancellation here. That's x cubed. Okay, so the next step is I'm going to multiply this x over 3 into everything. So, and then I'm going to separate the integrals. So this is x over 3 times x squared plus 1 to the 3/2 dx minus 0 to 1. And then the x's here will combine to give me x to the 4th over 3 dx. Okay, so not too bad. This first one is just a u sub. U is x squared plus 1. Du is 2x dx. Du over 2 is x dx. Okay, so when I do the substitution here, I'm going to end up getting the integral. X dx is going to become du, so I'll put the 1/3 out here. This would be u to the 3 halves, du over 2, so that's really 1/6 the integral, u to the 3 halves du. Alright, we got to change our bounds though, right? So when I plug 0 in, when x equals 0, u is going to be equal to 1. And then when x equals 1, u is going to be equal to 2. Okie dokie. So I got my new integral here. So then I do the integral, I get u to the 5 halves, put the 2/5, put the 1/6, plug in, cancel, cancel. Okay, so that gives me 1 over 15. I plug in 2 to the 5 halves minus 1. 1 to the 5 halves is 1. Okay, then I have to just do this right hand side now, but that's a lot easier. So over here, I'm going to end up with, and I'll actually keep the minus throughout here, x to the 5th. I've got the over 3. I've got the now 5 down here from 0 to 1. And then that's minus 1 over 15. I'm going to plug the 1 in and get 1 to the 5th is 1. I plug 0, that's just 0, not bad. And there we go. Do I need to simplify? Always no. Haha, we have calculators for this. So those are, oops. So that was the slides. What I want you to do is try to go through, make sure you can do these examples. There's more examples on the worksheet that I've uploaded, that I've worked through, so you can check those out and you know, ask any questions. I'll have Zoom office hours. If you like using the Discord, you can keep using it, but I'll officially be doing my office hours on Zoom. I'm going to be putting on more information about that, but I just want to keep reminding everyone. And I'll see you in the next video.